Okay, so we had two rocket designs. Initially, we had a very short, stubby rocket design that only consisted of one bottle with part of another bottle topped by a ping pong ball for our nose cone. And the fins were rather large compared to the whole bottle. And in general, we found that our center of pressure was too high, and our center of mass ended up being behind the center of pressure, leaving us with an unstable rocket that basically went nowhere. So we had a couple solutions. We decided that we were going to keep the nose cone because it was a pretty aerodynamic design, but we were going to reduce the weight of the fins, move them back. So we moved the fins back down on the rocket to move the center of pressure, which is where the sum of the moments on the rocket equals zero. We moved the COP down, which allowed us to put the center of pressure behind the center of mass. And you'll see over here what changes we made. So here we have the fins that are lower, and we had an overall longer rocket. And inside the tip, so this is the same nose cone as before with the parabolic shape, which through some research we found seemed to be more aerodynamic than a pointy nose tip shape. But inside the cone for our second design, we added 40 grams of weight, and that allowed us to bring our center of mass even higher. So we had a proper distance between our center of mass and center of pressure, which allowed the rocket to fly more stable. As with the center of pressure being behind the center of mass, it allowed for any air drag to correct the flight of the rocket rather than toppling it over while it's in midair. And in order to come to these conclusions based on of where the center of pressure and center of mass are for each of our rocket designs, we used Open Rocket Simulator, which was an online program that allowed us to make a rough sketch of the rocket itself and the materials that it was made out of. And it generated a point of where the center of mass and center of pressure are related to each other. And we used those estimates to dictate how we were going to make our final design.
In order to figure out how the thrust profile worked for the rocket, we tried to figure out how the work would change with time, and that ended up equaling the equation of how the kinetic energy would change with time. So we ended up with this equation of how the kinetic energy, or the velocity of the water leaving the bottle, would change with the mass. Using those equations, we were able to solve for the velocity of the water, which is completely dependent on the pressure between what was inside the rocket and the ambient pressure outside, and the density of the water. Then once we found the velocity of the water leaving, we were able to come up with another equation for how the mass of water was leaving the rocket per our time difference. And once we had that, then we were able to come up with the acceleration of water, and the acceleration of water times the amount of mass of the water that was in the bottle would give us the thrust force at any given time. Once we had the thrust force, we needed some way of calculating what the pressure inside would be at any given time. So we used the amount of pressure and volume that was in the bottle originally, and then we came up with an equation for how you could calculate the amount of volume that would be in the water at any given time, and based on that, we were able to find out what the pressure was at any given time. Once we knew what the pressure was at any given time and what the thrust force would be at any given time, we had to figure out what the acceleration would be on the rocket depending on the thrust force. So the thrust, that would be a sum of the moments equation using the drag force, gravity, and thrust would be acting the opposite way of both gravity and drag, and using that, dividing by both the mass of the water inside the rocket at any given time and the mass of the bottle, we were able to figure out what the acceleration of the bottle would be.
Then once thrust was completed, entered the next stage where we needed to know the acceleration of the rocket at any given time after the thrust. And that would be entirely dependent on the drag force and the gravitational force. But drag force changes depending on whether the velocity is acting upwards or downwards. So originally drag force is acting the opposite direction of the velocity as Vy is greater than 0. So the acceleration in x is unchanged, but the acceleration in y, it has a negative drag force. But once velocity becomes less than 0 and it hits the optimal height and starts coming down, the drag force is actually going to be keeping it in the air longer, so AY is going to have a positive drag force and a negative gravitational force. Then, once the accelerations were calculated for the whole thrust process and the post-thrust process, I inputted them into MATLAB, and using a while loop, I would adjust the mass of the water, the pressure, the x and y components, and the amount of, like, how fast the water was leaving the bottle during each time step. And then that would be one while loop for the whole thrust profile, and then there's a second while loop for once the amount of water in the bottle was 0, then it would enter the second while loop, which is as long as the bottle was above ground. It would go through another while loop using the accelerations we calculated previously for the post-thrust process. And based on those calculations, we came out with a graph that looks similar to this, showing the whole thrust profile as being basically linear, and then afterwards it dropping off and kind of coming down somewhere around 15 to 20 meters.
Our rocket design did not land on the intended target, which was roughly 60 feet away, on either of our first 2 official attempts. On our first attempt, the rocket did not lift off the ground and skidded straight across the grass for approximately 40 feet. Indeed, our launch angle was too low, and we didn't provide enough pressure to lift the rocket off the ground. Also, the bottle was not properly fixed to the launching pad, which resulted in a launch pad malfunction. On our scenario 2 for our second launch, the rocket lifted off and then suddenly lost stability, looped, and plummeted into our poor classmate Phoebe about 20 feet away. So in general, our rocket was unable to perform properly with the target being so close to the launch zone. So our test prior to the launch day involved much higher pressures and much larger launch angles, since we thought our target would be much further away. And it seemed that these conditions were necessary due to our hefty rocket design. After Paul left on launch day, we decided to test it one last time under the conditions that we prepared ourselves for, to suit our longer, heavier rocket. So therefore, we increased multiple parameters, such as the amount of water, the launch angle to about 60 degrees, and the pressure to 100 psi. And as you will see in the following video, the results were much different under these circumstances, as our rocket launched out of sight and was never to be found or seen again.
No, we're almost to 100. It just means the gas. Okay, 70. Oh my god! Didn't even watch.
One of the ways we could have improved our rocket was the older model was really short, but because of the weight of the fins and the weight of the water, the center of mass ended up moving below the center of pressure, which made it destabilize during testing. So then we moved to a larger rocket, but the longer rocket made it unstable with pressures that were too low. So instead, we could improve by making a rocket that was smaller, somewhere between both sizes, but had lighter fins and a heavier nose, so that the center of mass would move above the center of pressure, making it more stable during flight. A second way we could have improved was, instead of just testing for pressures that were above 60 psi, the ones that worked for this rocket, we could have actually tested a wider range. We would have found out that our rocket didn't work on pressures that were lower than that were required to get to smaller distances. And then one of the third ways we could have improved was when the rocket actually had water in it, the center of mass moved down because of the weight of the water. And we could have taken that more into account and realized that the center of mass is going to start a lot lower than we thought originally with just the rocket, because the rocket by itself is what we put into the program to figure out where the location of the center of mass was. And instead, we could have taken into account the water and then moved the center of mass a little bit higher to account for the mass of the water, which would have allowed it to be more stable during thrust.